Welcome class to our first lesson for the day. We'll be looking at organic chemistry, which is unit 1, and we'll be looking at ester specifically. And so, to start off, we'll be looking over this example over here. And so this is something we've already learned in the past, or you should know. If not, you can go ahead, pause the video, look through your notes review. But for now, we're going to go ahead and answer question number 1. And so what kind of organic structure is shown? This here is a carboxylic acid, and we can tell this by identifying the carbonyl group, and we remember through our notes that we know the general structure of a carboxylic acid. This is something you should know by now, and if you don't know, it'll be confusing when we proceed, so go back and make sure you understand the fundamentals. And so, moving on to question number 2, what is the IUPAC naming of this organic structure? This right here, if you want to count the carbons, 1, 2, 3, we know there's, what is his name? What is the acronym? Monkeys eat peeled. That means 3, so we have 1, 2, 3, P. So this is propanoic acid. So if you don't remember that monkeys eat peeled bananas, which is methyl ethyl propyl butyl, is very useful to know. So again, note that down. Moving on to our actual lesson, we're looking at esters. And so esters are made through the neutralization of a carboxylic acid. And so the H atom is replaced with an alkyl group. And so we can see over here that we have an alcohol and a carboxylic acid, which are reacted together to form our ester. And we'll go more in depth into this. You'll see in the next slide over here in the naming slide. So this right here is the general structure. And so it's important to note that you should understand what we're looking at here, because it makes this whole nomenclature part easier. I could sum up this whole thing just by saying that if you know where the carbonyl group is, you know where the carboxylic acid is. And so once you have that, you know that attached to the O here is your alcohol, because alcohols, they have the hydroxide atom, they have the hydroxide component, and so it's important to understand where this product is coming from and where the alcohol and carboxylic acid are actually coming from. And so you may notice over here that there's prime on the R, and this one there isn't. This is just to state that there's a different alkyl group which attaches to this location, so it's not the same alkyl group. And so you can go ahead and pause and read this, but the main point is you take the carboxylic acid as the second half of the name, which is the final half, and you remove the oic acid and change it to O8. And then the first half of the name, if you see number 1 over here, is where we take the alcohol and we just add that to the front of the name. And so, for example, if we were to go back and make our propanoic acid over here into an ester, we would get propanoate. And then it also depends on whatever alcohol is used, but you get the point. Let's say we use ethanol and propanoic acid, it'd be ethyl propanoate. There you go, that's a better example. And so, what are the properties of esters? So, due to the polarity of esters being less than acids, they are actually less soluble in polar solvents. So, for example, water. And so, another property is that in addition to the reduced polar bonds and lower intermolecular forces, it results in a lower melting and boiling point than acids. So what this means is that we know that you may or may not, but you should know from grade 11, is that intermolecular forces are what determine the melting and boiling point of a substance. And this is true because of the fact that how strong the bonds are between each molecule and how much energy is required to separate them is what matters. And so that is determined by intermolecular forces. And so we'll review this in the future lesson. I believe it's the next lesson, so don't worry if you don't remember too much. But the basic concept is that the more intermolecular forces it is, the higher the boiling point and the harder it is to melt, essentially. And then our next property of esters is that similar to hydrocarbon parents, esters with the high molecular mass are waxy solids, and a low molecular mass esters are gases at room temperature. And so as such, low mass esters can be characterized by odors, and we will be looking at those. And so over here you can see that only dipole-dipole interactions exist here, and so oxygen atoms are H bond acceptors, and so this is meant to show you how we have lower intermolecular forces than the parent alcohol, because they would have had the hydrogen bonding between the H and the O. However, we don't have that. So now the reaction of esters. So the first reaction we're looking at is esterification, and so this reaction is actually how esters are created. And so, as you said before, a carboxylic acid is neutralized with an alcohol, and it creates an organic salt, which in our case is the ester, and then there's a byproduct of water. So if you look to the bottom left over here, we have our carboxylic acid reacting with the alcohol, and we actually have a catalyst here, we have H2SO4, which is an acid, which is, make sure you note that down, you remember that, and heat. It doesn't necessarily have to be H2SO4, but for our purposes, we write H2SO4, so note that down. And so yeah, this is our reaction. We have carboxylic acid, alcohol, H2SO4, and we get an ester and a byproduct of water. And so this water can be then removed through the process of condensation, and so, but we don't worry about that for now because we're just understanding what exactly is going on. And so now there's actually a reverse reaction called hydrolysis. And so this reaction is the breaking of a covalent bond in the molecule through the addition of water. And so what happens is we have our ester and we add a base, and that separates our ester into our carboxylic acid in the form of a salt, and we get back an alcohol. And so moving on, we were going to talk about lipids and oils. And so lipids are a class of organic compound including fats and oils. And so they are formed through the esterification of carboxylic acids known as fatty acids, along with the alcohol component of glycerol. So as you can see over here, we have the fatty acids and glycerols reacting together. And so fatty acids are just long chain carboxylic acids, while glycerol is a 3-carbon alcohol bonded with 3 hydroxyl groups. So again, look over here, we have our 3 fatty acids, which is just really long chain carboxylic acids, and then the glycerol over here with its 3-carbon alcohol bonded. Yeah, you understand it. And so the ester is then formed through the esterification of these reactants, these two, and so we get something called triglyceride. And so therefore lipids are esters called triglycerides basically. Before we move on, my fault. A property of lipids that you may want to note is that the best known property is that they're insoluble in water. So for example, think about when you mix a salad with oil and vinegar, and you mix and mix and mix, and yet they quickly separate. It's because oil doesn't dissolve in an aqueous vinegar. It's because lipids are not water soluble because of their non-polar nature. And so this is true because they have the long fatty acids in the triglyceride molecules. And so these long non-polar chains overcome the polarity of carbon and oxygen bonds in the ester groups, and so it can't bond. So just make sure you know that property, but I'm sure if you just think about your salads, you'll know that property, so don't worry too much about noting it down, but it's just something you should know. Moving on to esters and soaps and detergents. So why are we talking about esters, and what does that have to do with the topic of soap and detergents? And so soaps and detergents are naturally made through the calculated reactions between fatty acids and glycerols. So the actual process is that oils are purified, blended, and mixed with sodium hydroxide rapidly before being placed into a heated chamber to undergo saponification, which if we go back, I don't know if I mentioned this or not, saponification is the process in which soap is made. I don't think I mentioned this, sorry, let me go back. Hydrolysis is the process where an ester is broken down, correct? And so when we want our soap, we want an ester of a lipid. We want a triglyceride. And so what happens is when this triglyceride is broken down, we get a soap as one of the as our primary salt. And so yes, back to where we were. Oils are purified, blended, and mixed with sodium hydroxide rapidly before being placed in the heated chamber to undergo saponification. We said that. And so a glycerol mixture is then washed with sodium chloride, and due to its solubility in water, it separates. And so what happens then is the glycerol solution is concentrated by evaporating off the water, and then it's purified through distillation. And so with this, the main point is that animal fats and vegetable oils and other substitutes are being tested and used to create different quality soaps. And so, for example, some higher quality soaps contain unneutralized fatty acids to improve the texture of the soap in the skin. And so the main point here is to understand that there are different animal fats such as tallow and vegetable oils such as, I believe I have in the notes over here, such as coconut and palm kernel are being used to create soaps in different ways. And so it's important to understand that while we may go to the store and buy soaps, there's still so much more going on chemically that we don't know about and that scientists are still testing. So moving on to our consolidation, for our esters, we will be naming this. So if you remember what I said before, if you can locate the carbonyl group, you know where your carboxylic acid is. And so we can go monkeys eat 2. So this is ethanoic acid. And then we go to the other side, we find our alcohol 1, 2. Monkeys eat. This is ethanol. And so when we put it together, we put the ethanol in the beginning, but it becomes ethyl. And then we go ahead and we take our ethanoic acid and we change the ending to OH, so we have ethyl ethanoate. And I do believe That is what this should say. ETHYL ethanol. Yeah, ethyl ethanoate. Correct. So if you got that, you got it right. And yes. Oh, for future references, because I don't think I said to pause, but if you're gonna answer questions and I don't pause, do go ahead and pause the video, see for yourself, and then go about the question. And so moving on to the next consolidation question. This is your homework. Actually, we won't be going over this, but your job is to draw these two compounds, propylpropanoate and butylpropanoate. But if you understand what we did here, and like you can even go back and rewatch the video and see the process we use, you'll notice that it's not that difficult. And so, oh, I believe there's one more. Correct, yes. And so this is not much of homework as much as for fun. You can even go tell your family, but go looking around your house for esters. Like, what scents can you find? So for example, there's ethyl ethanoate, which is the scent of pineapples. There's 3-methyl-butyl ethanoate, which is apples and bananas. There's octyl ethanoate, which is oranges. And so just go around your house and just think what kind of esters might be out there, because again, like, we don't think about soaps and how they're still being tested. It's a luxury, something we just go to the store and we grab. So just take a break, sit back, and think, how much chemistry is going on around me? And you'll realize how much you really don't know about what's going on in your daily life and how interesting it really is. Alright, so before we move on to this next lesson, which is intermolecular bonds and the physical properties, which is part of Unit 2, which is atomic structures, go ahead and take a break, pause the video, get a snack, go do those questions, let the information sink in, and come back, because we're moving on to the next unit. And so if you don't want to rush yourself basically and overload yourself with new information. And so if you're ready, we're going to move on. And so again, we're doing intermolecular bonds, which is the physical properties of it, and this is part of the atomic structure unit. And so before we begin, minds on, you know the drill. What is the difference between the soap and detergent? And so this isn't much of a question as much as something interesting for you to know. And so dating as far back as the 70s, 80s, in ancient Rome, there have been documents of soap being found, which is crazy, because like, soap, you would think that this is some it's not a, how do we put this, it's not a revolutionary invention, but it's definitely not something you could imagine they had back then, because there was the Black Plague and sanitation was a major issue, and the way that soap, it was a luxury. And so if you read on, you'd see that soap was made by specialized workers. It was a simple luxury, and it wasn't being mass produced until the 18th century. And then meanwhile, detergents were trying to be created in the period of World War One. And so you can see detergents are a far more new, more modern concept. And so the reason why they were actually invented was because soap ingredients were consumed faster than they were being placed. And so a synthetic alternative had to be found, and that was detergents. And so while soaps are made through natural ingredients such as plant oils and acids from animal fat, as you may remember from the previous lessons, detergents are being made from man-made imitations. And so throughout our lessons, we'll be referring to them as the same thing, because chemically speaking, they do have very similar and essentially the same properties. So if you ever hear me using soap and detergents interchangeably, know that it's intentional, because they're very, very similar. And so one of the differences, however, is that detergents contain surfactants, which is a short form for surface active agents. And so these are just versatile, and they're able to effectively clean through the manipulation they're able to clean through the manipulation of water surface tension. And so that's the primary focus of this lesson. So we'll move on. But before we move on, we're going to review a little bit some grade 11 stuff. So there's strong intermolecular forces, which is ionic interactions and dipole ionic interactions. And then there's weak intermolecular forces, which are van der Waals forces. And so we have hydrogen bonding, dipole-dipole, and then London dispersion. And so these are going from strongest to weakest. So ionic being strongest, London dispersion being weakest, and among the weaker, hydrogen bonding being the strongest, and again, London being the weakest, London dispersion. And so moving on, we can go and actually, here, let me go ahead and review this a little bit. Let me get my, where is it, paint. And so over here we have our crystal lattice structures. And so essentially what we have going on here is we have these negative dipoles and positive dipoles, and these are very, very, very tightly knit. And so we have bond, 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 and it's this really sturdy structure, and they are very difficult to break, which is why they are our stronger forces. And so meanwhile we have our London dispersion forces, which are London dispersion forces essentially my apologies. London dispersion forces are essentially forces you find no matter what, because they happen randomly. They occur as you have, okay, for example, we have this over, go ahead and make this larger. We have this example made over here. It doesn't matter too much, but this is our current structure. However, at any given moment, because remember that our atoms, they're all always vibrating, so at a random moment we may have it so that it ends up like this, and so now suddenly these two are forming a bond. And so again, it's very random, because they're rapidly vibrating, and so these forces just occur at a random. It's there, but it's almost as if it's what's the wording? The main point is there's it's not a calculated force as much as it randomly appears always. And so over here we have our second one. We have dipole, and so we have the positive dipole and negative dipole, and then down here we have hydrogen bonding, which don't know why it's reversed ordered, but yeah, this is hydrogen bonding. And so the way hydrogen bonding you should remember is NOF. So hydrogen bonds with nitrogen, oxygen, and fluorine. And so yes, and yeah, if you don't remember, you can go through your grade 11 notes, because I don't want to spend too much time on this. So yeah, and so our primary focus here is surface tension. And so what is surface tension? So let's look over here. Have you ever seen these water droplets, and you notice that it beads up? It's not a flat droplet. And so the droplets of liquids are appearing in the form of a bead because of their intermolecular forces. And so these molecules are being actively vibrating against each other, and they're being attracted to one another by the bonds formed between each molecule. They're hydrogen bonds. And so this includes hydrogen bonding between the hydrogen and oxygen atoms. And so the reason why it forms this bead shape is because some of the molecules are not fully surrounded by the same molecules. They have air, the upper layer. So for instance, let me go ahead and get this again. We have all of our water molecules bonding, having fun, disco party, interacting with each other. But this outer layer here, these guys, they are exposed to air, and so they don't want to interact with air. And what happens is that they pull themselves towards the center. And so now you have, they're pulling inwards towards the center. Let me use a different color, maybe blue. They're pulling, and so now magically we have got this bead shape, and which is why our water beads. And so what actually happens is it sort of forms like an elastic membrane. So it's like it has tension, like a rubber band type of thing. And so yeah, the resistance to increase the surface area is the surface tension as the molecules pull tightly to form a bead shape. That's the main thing. And you can see over here that these bugs, I believe they're called water striders, they actually use surface tension to their advantage, because they have these long legs and they distribute their weight so that the surface tension doesn't break, and they're actually able to walk on that elastic membrane. And I do believe that they also have hydrophobic hairs on their legs, which essentially means that their hairs, their bodies will not bond with the water, so they literally will not break the shape. And so you'll understand this more in the future, in the next few slides. So here we are. There's cohesion and adhesion. These are some properties of water. So cohesion is, there's cohesive forces exist between the liquid itself, and it is the tendency of the liquid to stick to itself. And so what this means is that the molecules are going to stick inwards, and which is what we have our beading here. And so what happens is we form a convex meniscus, and so we call this curve here a meniscus. And so in this example, it's mercury in the glass vessel, as it says here. And this is true because mercury atoms have stronger cohesive forces than adhesion forces, and so we get this convex meniscus. And meanwhile, with the adhesion forces that exist between liquid and its surrounding, so you see cohesion is it bonds to itself, versus adhesion is sticking to other things. And so more likely than not, it'll be its container, because that's what you'll have water contained in. And so this causes a concave meniscus to form, and you can see here the water is actually sticking. I can't zoom in, I'm sorry, but you can see here the water is somewhat curving up. You can also see it slightly here. it's trying to climb the walls is the main concept. And so the cohesive forces of water are weaker than the adhesive forces between the water, and so the positive dipole of the oxygen so a concave meniscus is formed. And so what is the application of this? And so some example you can see is this is being applied for trees and other plants as they're transferring water throughout themselves through the property of adhesion. So go back here. Adhesion, we note that it's climbing up. It's climbing up the sides of the glass. So in this case, plants have something called a xylem, which is they have xylem and phloem, which is their way of transferring water and nutrients throughout their system, which is more biology, so we won't go into that. But the primary point is that it's utilizing this concept of adhesion to get the water up itself, and I believe it's called capillary action, which I do apologize is not in my note here, but that is what it's called, capillary action. And so moving on to melting and boiling point, which we touched on in the previous lesson if you do recall. But in corresponding with the intermolecular forces, the melting and boiling point of liquids are affected as well. And so with stronger intermolecular forces present, a substance requires more energy to reach its melting or boiling point. And so as such, as the substance size grows, its melting and boiling point increases. And so this is true as atomic radii and nuclear attractions change as the size of the molecule vary. And so we can look over here. It's ice, boiling water. These are just general images just to get the concept of melting and boiling in your head. But you can actually see that intermolecular forces, as it increases, the temperature required to melt or boil changes. So I believe that these are boiling point. Yes, boiling point of alkenes versus similar to alkanes. And so what's happening here is we are increasing carbon atoms. And so let me again get my painting software, and I'll make us have a larger area to paint. So let's say we have a C and a C here, and we have all of our H's filled in. I'm not going to fill them in, but you have this here. And then you compare it to, and again you have all your H's here. Which would you say had the stronger intermolecular forces? Now you could say that, okay, they both only have hydrogen here. They have the same bonds. They don't have hydrogen bonding because there's no oxygen here, there's no nitrogen, there's no fluorine, so there's no hydrogen bonding. They could have dipole, let's say, assume they did, but they both have it, so it's the same thing. And in London dispersion, they both have London dispersion, so it's the same thing. But that is where this primary concept of increasing carbon atoms does in fact increase intermolecular forces, because remember, it's not as much as the strength of the individual, but the fact that there's bond here, bond here, bond here, bond here, bond here. There's all these bonds, and then the fact that London dispersion is very random, so there's so many smaller bonds being formed, while this one has a lot fewer. And so intermolecular forces, don't forget, they add up. They really do add up. It's the smaller quantities of them that add up to build higher intermolecular forces. And so connecting intermolecular forces to soap and detergents make water wetter. Now you might be saying, what does this mean? How do you make water wetter? And so detergents are surfactants, as I mentioned, and so this means that they're effective at reducing the surface tension of water by pushing apart the water molecules. And so they do this by using their hydrophilic ends that likes water, which you can see over here is these heads over here which grab onto the water. And so they actually push at the surface tension, and this breaks it. And so meanwhile, they have their tails over here, these zigzag looking things. These are hydrophilic tails. And so these tails are able to bond to grease and form small structures called micelles, which if you see in this drawing over here, this structure is a micelle because it's sort of like the detergent cells, the structures, they surround the grease. They surround the grease and they form a micelle. And so you can think about when you're doing dishes, when you rub water on it, nothing happens, but you put soap and suddenly it's scrubbing up. And so what's happening here is you're having these hydrophilic tails attaching to the grease, the oils, and then when water comes, it attaches and it's pulled away. As you can see here, see? It attaches to the oil, and then water comes and pulls it away. That is the whole concept of detergents. which is why it's so unique, why just simple water isn't enough, because it doesn't have that bond. And so yeah, the main point I want you to get out of this is that detergents are able to break the surface tension because of their hydrophobic ends pushing up against them, and then their hydrophilic ends are then able to bond with the water after it's bonded with the intended thing to be removed, which is going to be oil and grease in this case. And so consolidation. So you have to ask the following questions using your knowledge of intermolecular forces and the corresponding physical properties. So number one, I'll do it with you, and then you can, or perhaps we'll go over. We'll see. So number one, if intermolecular forces are stronger in a liquid, will it be smaller or larger? So what this means is, where's paint? Paint. It's messy here. Okay, over here. So question is, if intermolecular forces are stronger in a liquid, will it be smaller or larger? So let's say we have this liquid here, and we have, oh wait, this is kind of the same, and we have this one here. Which one has the higher intermolecular forces? And so I'll answer this with you. If we go back to, I believe it's this slide, right? Surface tension, yes. It's pulling itself inwards. So the more tightly squeezed, see the resistance to increase the surface area as a surface tension. So essentially, where was the paint? This one would have the stronger intermolecular forces because it's more resistant. It's pulling itself more in. So rather than being more elongated, it's become taller. It's become a lot more. The forces are pulling itself in a lot more, and it's sort of climbing slightly, yes, because of that. But versus this one, where it's a lot weaker of a pull. Think of it as these guys are pulling them in, making it skinnier. Yeah, my bad. These drawings are a little messy, but I hope you understand that paint. The point is, the smaller the circumference, which is what I put in the hint, I believe. Yeah, the smaller the circumference, the smaller it is, and taller it is, because they will correlate. Explain how a paper clip is able to float in water. You can do this on your own. The primary concept again is surface tension. You should know this by now. But why is this not obvious? I'll answer this question with you too. It's not obvious. This is not obvious because density. Paper clips are metal. They're solid. They're a lot denser than water. So naturally speaking, they should sink. But again, we know that because of this property of water, its surface tension, its resistance, its elastic membrane, it's actually possible for a paperclip to float. And so then this number 3 here, we kind of answered this. You should have to answer this yourself, so we'll go over it again. What causes the change in boiling point and melting point as hydrocarbon chains increase? And this is the quantity, not as much as the individual strength of the force, but the increased amount of small intermolecular forces that adds up. So we're going to go ahead and move on to the next lesson. But before we do that, again, take your break, get water, let the information sink in. Hey, get your water and look, don't make a mess now, but spill a drop and you'll see the beating. It's really interesting. And if you look at this picture, it's a special fabric here. It's a hydrophobic fabric that wouldn't let the water spread out. So it's meant to bead here, like so you won't get as nice of a bead. But even if you look at your sink, now don't do this because we don't want to waste water. But if you see a water droplet dripping, you would see that, like even in cartoons, you know this. Water drips like this. That's its surface tension pulling it in. It doesn't fall like this. Like it's not a solid line. No, its surface tension makes the shape of a water droplet. So now you've learned something more about water, which is something you drink every day, or at least you should be. Get your fluids. And yeah, go ahead and go on your break. All right, so welcome back from your break. I hope that you were able to understand the previous lessons. Don't just go back to lesson 2. Go back to lesson 1. Make sure that all the information has settled in your head and you understand it all before you move on, because this lesson is a pretty short one, but the consolidation question at the end there will kind of test your knowledge. So yeah, but if not, we're gonna move on. So this is thermochemistry, which is unit 3, and it will specifically be looking at bond energies. And so for the minds on, again, it's not something you're going to solve as much as it's the concept to understand. And so ethine, which is C2H2, is a hydrocarbon compound that burns to produce flames at temperatures greater than 3000 degrees Celsius. And so at such high temperatures, it's possible for ethylene mixed with oxygen to cut through steel. And so bond energies can be used to estimate the enthalpy change of any chemical reaction, and in this case, it would include the amount of energy associated with the combustion of the ethylene, and so there's the reaction of the steel having its bonds broken, and many more. And so the main concept to get here is that 3000 degrees Celsius is very hot, and it's interesting how thermochemistry, can be used to calculate just exactly how much temperature, how many kilojoules are being displaced here in this reaction. And so enthalpy is what we're going into. So enthalpy of a reaction is directly proportional to the bond energies, and so bond energies are the amount of energy needed to break apart 1 mole of a given chemical bond. And so this value can be determined experimentally or carefully researched using data charts, and scientists have been making these data charts for different substances for ages, and they'll keep on being researched. But the way we'll be looking at is through experimental calculations. And so therefore a reaction involves the breaking and forming of bonds, and the strength of the forces holding the atoms together is what determine the energy required or released during a reaction. And so basically the main thing to understand here is that reactions will involve either breaking or the creation of new bonds, and what we're here to understand and calculate is the energy required to create those broken bonds or form new bonds. And so here we have a table here, and so you can see that to break a hydrogen-hydrogen bond, it would take 432 kilojoules per mole. And so you can go through all these if you want in your own time, but you don't have to have it memorized for our purposes because we're just practicing. However, just through practice, you'll eventually get something to stick in your head. But if you specifically look over here, I want you to note that you have C and C, we have carbon-carbon bonds, and over here, I do believe we should find carbon-carbon bonds 247 and then 614. And it says note that these are multiple bonds. So this has a double bond here, and there's triple bonds, and these all have different enthalpy values. And so it's important to note that different bonds have different values. And so whenever you're answering problems, which we'll see in the next few slides, be careful of what you're looking at. And so this here is a multiple bond being broken apart, and so you can see that there's the 2 bonds here. And so first we have the 1 separated, and then we go back into we bring this back into the reaction, and we have the second one separated. And so to calculate the bond energy, we'll see is bond energy 1 plus bond energy 2 divided by 2. So you average it out. And so to give you a more proper explanation, this is the additivity of bond energies. And so naturally compounds with multiple bonds exist, as we just discussed. There's all these, there's CC, triple, there's CC double, there's C double, carbon double bonds, carbon triple bonds, oxygen double bonds, carbon oxygen double bonds, carbon oxygen triple bonds, and so on. But the main point is that you calculate the bond energies for these compounds by using the sum of all the energy absorbed or released from each one. And so for example, the decomposition of methane, we have CH4 decomposing to CH3 plus 1 hydrogen. And so we want to go back to here. Actually, sorry, no, these are experimental values, so you wouldn't be able to use this chart here because the 435 we can go look for between. It'd be H. We don't have it. 435. You keep looking. It won't be there because these are just experimental values we've been given for now, just for the sake of understanding the concepts. And you can see how 435, 453, 425, 339, these are all different values. But note that each time we are breaking the bond with the hydrogen. And so in the end, we total these values to get 1,652 kilojoules per mole, note the units, and then we average it out to get 413. And so if you look back, going forward, let's go back. Where is it? 413, CH, 413, 413. That's how it's experimentally calculated. And then there is enthalpy and bond energy calculations. And so to find the enthalpy value, which is delta H, in case you don't remember, is the sum of energies required to break bonds, which is positive, plus the sum of energies released. And so that's what this symbol here is, the sum. And so we move on to the next, where it's sum of the moles times the bond broken, so the enthalpy of the bond broken, minus the sum of the moles times the the products formed, the bonds formed, and so we can further the reaction, the formula to be moles, some of the reaction bonds broken, minus the moles times product bonds formed. So this might be a little confusing, which I get that it's like the sum symbols in the words, it's not numbers, so it's a little confusing. So when we move on to this example, it'll be a lot more clear. So example, we're gonna do this together, we're gonna have the whole thing explained. So the question is to estimate the enthalpy using bond energies. And so this is our reaction here that we're gonna be estimating the enthalpy of. And so we have hydrogen gas plus fluorine gas forms hydrogen fluoride. And so note that this is a balanced formula. This is a balanced equation for us. We have H2F2 and we have 2H2F. So everything is balanced here. And so that's kind of a trick you'll see in the future. Make sure everything is balanced. And so our first step is to establish the information given and information needed. So all we've been given so far is the fact that we have hydrogen and fluorine being bonded together, and the fact that we have 2 moles. So we don't have much information, and so we can fill it out. We don't know this. We don't know the enthalpy. We don't know the values per mole, the kilojoules per mole of that. So we leave that as question marks for now. But we do know the molar value, so we go ahead 1, 1, 2, 1, 1, 2. We can fill that in. And so remember that our primary goal is to find delta H. And so step 2 is to check bond energies table for values and fill in unknowns. So we can go back here, or before we go back, let's see what we're looking for. We want to have a HH, FF, and HF. So, and these are all single bonds, note that. So HH, so 432, HF is 565, and I believe our last bond was HH, HF, and then HF. I forgot, but you get there. You can go back and forth. On the test or in the quiz or whatever, you'd have the information in front of you. So we have 432, HH, we can double check. We'll do one at a time. 432, yes. HF is 565, I remember that one. 565, yeah, HF. And then FF is what I forgot. FF. Fluorine, where are you? It's a little annoying, but you'll get used to it. 154 here. There you go. And we already had that all filled in for us, but just for the sake of practicing, now we have all of our data filled in, and we can actually go ahead and use the formula. And so now we have this confusing formula with words, and we're going to rewrite it into this. So now we have it as the moles times the value we just found here, plus moles and the value we just found, and so you get the idea. We'll fill it in, and it's very important that you put your units down, because it becomes very confusing to keep track of them, because which I'll show you in a second right now. Because don't forget that, where is paint? I'm sorry, paint. Don't forget that in this case, while we have moles and kilojoules per mole, so we have mole times kilojoule per mole, so this is our 2 units, that these cancel out. So our unit becomes kilojoules. So this is actually saying kilojoules plus kilojoules plus kilojoules, which you can see we move on down here. It's kilojoules plus kilojoule plus kilojoule. But let's not get ahead of ourselves yet. And we can go through the whole thing. So we have the 1 mole, we knew that. And then we have the value. And then 1 mole, we knew that. And then the value. And then 2 moles we knew. So this is where it becomes different. So we realized that the end value is very important, because if we hadn't had this here, we wouldn't get 1,130. We'd have 565. So be very cautious of your mole values. And so it's simple. This is very simple math. It's just inputting numbers into the equation. And so we resulted in negative 544 kilojoules. And so last step is to write a final statement, a therefore statement. And so we have, therefore, the reaction with reactants of 1 mole of hydrogen gas and 1 mole of fluorine gas, and the product of 2 mole hydrogen fluoride results in the release of 544 kilojoules of energy. Now note that I didn't say the release of negative 544, because that's incorrect. You can't release a negative amount, because in that case it'd be absorption, because negative times negative is absorption. So be very careful with the way you word it. And so the simplest way to put that is in brackets delta H equals negative 544 kilojoules, just to be clear. And your therefore statement doesn't have to be this wordy, it doesn't have to say all that, but just make sure it's very clear how you word it. And so now, connection to soap and detergent. It's discussion time. My bad. Let me get a sip of water. You guys can go ahead, pause the video, take a sip of water, get a snack. It wasn't too much information, but it's new information nonetheless, so let it sink in. My apologies, I'm back. Okay, so what have you learned about soaps and detergents so far? And so what type of bonds can be formed or broken to be related to this unit of bond energies? And so before I drag this box down, you can think now. Naturally, this isn't a live thing, so we can't get answers, but here are some things to guide us and answer for us. So what have we learned about soaps and detergents so far? We've learned, if you want to go back, we can even look back. We've learned about the way that they're made. We've learned that they're still being tested. We learned how different animal fats and vegetable oils being used have different outcomes and different qualities and different textures. We learned that extractive forces are being able to clean and do things that water can't because of the fact of its. We learned that detergents have their hydrophilic tails, which are able to bond, and then their hydrophobic tails, which break surface tension, and so they do things that other substances can't because they don't have the same characteristics as detergents. And so then we also learned. What did we learn? We learned that when detergent and water interact, we do not know. Don't do this yet. Okay. Main point is, we learned that there are many bonds which can be made and broken. So primarily, this is the primary focus of bond energies, because we want to look at how the bond between the oil and the fabric is being broken, and then the bond between the water atoms and the detergent are being formed, and the way that we have enthalpy. And so this is what I want to reveal here. When detergent and water interact, an exothermic reaction can be seen. And so you actually test this at home. So if you want, if not, you can just believe me. But if you want to test it, but don't go overboard. You can put some solid or powdered detergent in your hand and add a few drops of water, and so you should feel some heat being released. And now be sure to wash your hands because you don't want to put it in your mouth and get sick or anything. And the main point is that this is an exothermic reaction. Heat is being released. You can feel this heat. And so it's so interesting how bond energies can be applied to things like simply doing your laundry, washing your hands, because thermal energy is being released everywhere, all the time, many different reactions. And so it's very important that we understand these formulas, and we understand how to use these tables, because without these specific values, you won't be able to find the value. There's no other way unless you were to use a chart that's been predetermined by scientists, in which case it's a whole new method, so it just doesn't work the same. And so this is your homework now, which is exact same things we just did here. So you can go ahead and pause the video, go back, but do try it yourself, because you want to be able to use this on your own. You don't want to have to keep going back. So maybe go ahead for the first one, try with the video, and the next one do on your own. But hint, this is a hint, which technically I should have blocked off, but we left it there. But check error. My apologies. But check if equations are balanced. So let's look at the first one. H2Cl2. There's an issue here. It's not balanced on the right side. Let's look at the next one. N2Br2. Now we have 3 nitrogens and we have 3 bromines, however you want to say bromines. But it's not the correct amount, so you have to rebalance these. So you can, it's take a few seconds. You should understand it from grade 9, I think, or grade 10, and you should get the hang of it. But that has been the 3 lessons. And so to tie it all together and say, why do we care about all this? I'll be talking about the implications on society and the relevancy of soaps and detergents. And so the primary focus why I focus on this is I selected a media source which talks about how detergent is being studied by scientists and how it's still being made more efficient. How we are making, if we want to go back to this, how we're making it required of less water to remove the same amount of oil. And so this is important because of climate change. Climate change is a major issue for humans in the world. The world is it's being destroyed. Climate change is a major issue because ecosystems are being destroyed, resources are being overfarmed, overcollected, and people are wasting. Resources are being needlessly consumed, and people are neglecting their duty to the earth. For instance, look at this picture here. So much garbage is in our oceans, and these our animals, our ecosystems, they're entering them. They're eating this garbage, not knowing better, and they're dying. We are having many animals go extinct, especially in the Arctic, which I believe in the next slide. Yeah, climate change is insane, and people aren't doing enough. They aren't realizing that, yeah, there's factories, vehicles, and other large sources that are creating greenhouse gases, but just the small things we do, like leaving your sink, letting it running, wasting food, and many other smaller actions are adding up to have major effects on the earth. And so it's very important that we understand soaps better, and we find out how we can use less water, use less resources to clean our products, because unfortunately, or fortunately rather, hygiene is a part of our lives, and so we're going to use water to clean our clothing. But what matters is how we learn how to maximize our efficiency of your detergents and reduce the amount of water being used. And we also need to find ways that this water can be clean. It's not contaminated, and so in the unfortunate event that whatever water spills out and an animal consumes it, it's not poisonous. We don't want to have our crops being soiled, or our crops and soils being ruined by chemically infested waters. And the point is, soap is important. We're going to keep on seeing in our lives I don't think soap is going anywhere. Humans need soap. We need to be clean, and so it's very important that we keep on studying them, understanding them. And so why? Because I'm not going to read through all these facts. You know this. The temperatures are increasing. The ozone layers, the hole is getting bigger. We're having more UV rays getting in. The sea levels are raising. The acidity of the ocean. So look at this picture here. As the atmospheric concentration of carbon dioxide is increasing, it's being dissolved into the water, and it's increasing the acidity of the water. And so very gradually, which it's not an instant thing, but that is the issue. It's not stopping. It's not going backwards. It's only going forwards, and our waters are getting more acidic. And so if you want to go to the site, that epa.gov, which is where I got these specific things here, but we know these things, and yet people aren't doing enough. And so it's very important that using the media source selected, which is a YouTube video, which you can find if you would like, it's important to understand how simple things like soaps are so relevant to us, and how chemically understanding them and learning and understanding the importance of making them more efficient and continue to study them and not just settling for what we have will help make a difference, because less water will be wasted, and we will be a lot more we will be a lot more environmentally, my apologies, environmentally aware. And so, yeah, these are my final words. I hope that through these lessons you're able to understand esters, soaps, and understand the importance of why we need to study soaps, because our earth is dying, and it's not going to stop unless we realize the small things, like how our soaps are made, how we we put garbage in waters, and how we let our sinks run are adding up. Because like the ancient molecular forces, yes, there's the London explosion, a very weak force, but the more carbon chains, the more people we have throwing their garbage to waters, the more smaller things we have that are adding up, it's having a large impact. And so that's my thought I leave to you. How can you make a change, and how can just understanding how soaps are made help make our earth healthier?